Hello, everyone. I'd like to welcome you to the webinar series designed for CMI and by CMI. I'm Cynthia Howell. I'm the Education Workforce Development Manager at Colorado School of Mines. And today I'm going to be your moderator. And so I'd like to tell you a little bit about the webinar today. And Sam, if you move the slide forward, thank you. Our webinars are hosted by Colorado School of Mines. If you have a suggestion for a future webinar, we're always looking for topics. Please don't hesitate to add that to our exit survey or go to this website here. This is a public webinar, and it is going to be available in 2 weeks. And at that time, there are 3 sites. You can go to our YouTube, you can go to our cmi.aimslab.gov and actually get the webinar information. So questions. We are going to hold questions to the very end, and they can be typed into the Q&A box at any time. And I do encourage you to do that. As soon as you have that question, go ahead and queue up that question, because the presentation happens and we're ready to go at the end with answering your great questions. So they'll be answered following the presentation. Now I'd like to introduce to you our presenter today. We have Sam Palumbo with us. He's the VP of Business Development for Mineral Processing at Disa Technologies. He brings over 2 decades of experience and also in many leadership roles with Disa. He holds his MBA and has an exceptional track record in leadership and business development in mining. And of course, he has a couple of other companies that he's been with, Weird Materials and Derrick Corporation, and brings all of that experience to us today in his presentation. I don't want to take any more time. So Sam, why don't you take it away here? And we're looking forward to hearing from you.
Well, thank you, Cynthia, and thank you for that warm introduction. Also, thank you to Maureen for helping us set this up today. I'm happy to be with everybody here. I would be remiss if I didn't also mention that our Global Sales Director, Tim Lundquist, has had his schedule free up this afternoon. And Tim, who specializes in bringing emerging technologies to the mining sector, has 20 years across the mining industry and has worked in the past with myself at Weird Minerals as well, will join us for the Q&A session and be available as well. So with that, let's get started. So what I'm going to do is just go over a brief company interview. We'll do an introduction into the HPSA technology itself, what's happening around the product development and application overview. And then we'll also take a look at testing and pilots and case studies. As Cynthia mentioned, we'll then close out with a Q&A session. So before we dive into the technology, let me introduce you to some of the team and what we've been up to here at Disa. So Disa Technologies was founded in 2018 by Grayson Buckingham and John Lee, really 2 visionaries who saw an opportunity to transform mineral processing. And in just a few years, we've gone from concept to commercial deployment. We're backed by $48 million in investment. And have grown from 7 to 35 employees in just a short year, with an additional 20+ employees planned for hire in 2025. We have a highly experienced senior executive team with over a century of combined years of experience across both the mineral processing business unit and uranium recycling. So it's been a fast ride, and really we're just getting started. Now, at the heart of our operations is our facility in Casper, Wyoming. This is where really innovation becomes reality and where the tinkering and the product advancements take place. We've got dedicated spaces for heavy assembly, testing, shakedown capabilities, and our lab in Colorado is where we conduct much of our R&D, our CFD modeling, and where the bulk of the sample testing takes place as well. So from road taps to filter presses to XRF and our batch units, this is where the bulk of the sampling takes place. And when further sampling or testing is required, like ICP or XRD, fire assays, we do have strong relationships with third-party labs at our disposal to expedite any testing requirements. So let's get into what HPSA is and really what it does. It is a mechanical process. There's no chemicals, there's no grinding media, just really controlled high-pressure collisions that are liberating minerals based on their intrinsic properties. It's a surgical approach, really, to breaking rock. It's focused, efficient, and it's also repeatable. With 5 US patents and 10 more globally, it truly is a novel way to unlock more value from the ore. And really what stands out in the chaos occurring, if you will, isn't random, it is quite precise. So the HPSA targets coarse particles, breaking them into their weakest points and leaves the fines behind. That means less grinding, less waste, and much more control of the process. And here you're seeing a visualization of what's happening as the slurry streams are leaving the impinging nozzles and colliding. So this is all happening inside the collision chambers, which you're seeing here in the animation or the video, if you will. So picture 2 streams of slurry slamming into each other with force, and precision is creating these microscopic fractures. So it's particle on particle liberation. And really that's the key to maximizing the liberation. Again, no chemicals and no grinding media is used in the process. So again, this isn't just a concept. It really does translate to real numbers. We see up to 80% cost reduction, 50% in energy savings, and 98% waste neutralization. So we're talking about transformation, not just in efficiency, but in sustainability. Here's what that looks like in action. If you take a look at the copper minerals trapped in quartz and orthoclase, you can see that they're completely liberated. So HPSA breaks the bond and really sets the target minerals free. And then they can go on down the line for further processing and separation and recovery. Now, if we take a look at the impact of energy consumption, we know that the grinding circuits are really the energy hogs of a mine space, with up to 53% of the mine's consumption of energy. So by integrating HPSA, we introduce, or we can reduce a number of downstream units of operation. That results in a streamlined circuit and delivers more with less, essentially. And you're seeing that here, where we're able to upgrade to 75% versus 55%, and the ability to eliminate flotation banks or attrition cells, and that helps bring the power draw down across the entire plant. So if we compare this to legacy systems, HPSA, you shouldn't consider HPSA as a radical disruption, rather a safe and logical improvement. It's fewer parts, it's safer operations with drastically reduced downtime. It's cleaner, it's uncomplicated, and it's far more efficient. Essentially, we're replacing brute force with intelligent impact and selective liberation. I mean, if you think about it, a ball mill was patented in the early 1800s, the SAG mill in the 50s, and the HPGR later in the 70s. So I think it's more about, we are ready to make improvements into the industry. We are ready to bring emerging tech to help become more efficient, bring down energy costs, create a more sustainable flow sheet, and HPSA allows us to tackle this. Now, if you take a look at where we're at from a product development standpoint, We do have available units currently ranging from 1 ton per hour to 50 tons per hour. And we do have a number of units ready in our scale up path. Recently, we've also been awarded a $8.5 million grant through the Wyoming Energy Authority. And that will allow us to now really ramp up scale and bring larger units online here later this year and into 2026. From an installation perspective, it's really a plug and play system. The units are modular, they're skid mounted, forklift friendly. Everything really that you need is built in, the piping, the controls, safety features. There's no foundations required. As long as we've got a flat, stable surface, then away we go. And then once it's on site, it's extremely quick as far as getting from hot commissioning or from installation to hot commissioning. It's clean. It's really designed to minimize downtime and maximize results. We're really wanting to not be intrusive of the existing operation, especially when we're talking brownfield. We want to take in the incoming slurry, and then we have an outgoing slurry as well, which can go down further in your process. So really minimizing disruption to current operations, allow us to come in and test and move into multiple streams across the flow sheet as well, with minimizing disruption to the day-to-day business. So here's how our full circuits look at scale. These are 10 ton per hour units that can go out into a remediation, a waste rock reclamation site, and operate as a full circuit. They can also be integrated seamlessly into an existing circuit, relatively small footprint with a really significant impact. And HPSA has been proven quite successful and has shown amenability across a variety of ores. More than a dozen applications have been tested to date. Now, certainly not as many of you know in our experience, we don't need, not every application behaves the same way in every deposit or every geography. So certainly plenty of test work still to be done and plenty of opportunities for us to be able to do that. But I think we've proven to date that it is quite amenable across a variety of ore types, and we continue to add to that list. The lab is quite busy month to month, and we certainly welcome the opportunity to test more ores and test from different deposits as well. Now, HPSA does handle a wide range of conditions as well. So from a percent solids perspective, anywhere between 0 to 55%. It's essentially what the centrifugal slurry pump can handle. That is what we use to pump the slurry through the impinging nozzles. And from a PSD perspective, you're looking at 10 millimeter to 20 micron based on the current scale of our units. Now, as the units scale up, so too our ability to take larger top sizes as well, which will avoid plugging the nozzles. So with scale up will come a bigger range of PSD and capability of solids handling as well. Today, if you think about the size reduction ratio, roughly 10 to 1, but that often depends on the cut size as well, which could allow it to be even greater. From a placement perspective, it's really the client's call in the end, whether it's feed replacement or cyclone underflow, tailings. HPSA is flexible in the sense that we can find where it best fits in a circuit and apply it where it's going to have its largest impact on a flow sheet. Really, it's like a Swiss Army knife, if you will, extremely versatile. Think about it as a process improvement technology, not so much a direct replacement of existing grinding technologies. It really does work in unison. So whether that's mill bypass and you want to increase plant throughput, and liberation, or you want to extend mine life and look at remediation and reducing tailings impoundments. So quite flexible. When we do get a unit to site, it does have the ability, because of its modular design and relatively easy plug and play setup, we can move it and test multiple streams. So from an on-site testing perspective, we do have the ability to bring it on site, quickly test multiple streams. As I've mentioned, the units are skid mounted, forklift pockets, really just need a welding power supply, simple tie-in, and allows for real world testing on the site's materials, right at the site, quick results, small footprint, again, minimal disruption. And especially in the sense if there's a lab on site, we can get results from our testing much quicker than we would back and forth samplings to our lab in Colorado. So we often encourage bringing a unit to site and conducting testing there to speed up the results cycle and get better, quicker feedback. So just before we dive into some of the results, I just a quick note to mention that the case studies are based on real testing. They're anonymized to protect the client confidentiality, but the numbers are real and the sites are real. So if we begin with uranium remediation, before HPSA, uranium was spread out across the mass profile, as you see in the graph to your left. And then after HPSA, you're going to notice that 93% of the uranium ended up in just 15% of the mass. So what does that translate to? Safer storage, better economics, and huge environmental wins. Of course, the EPA agrees. You can see some of the validated associations there in the bottom right. Over 2 years of testing showed up to 98% reduction in contamination with no leachability, plus up to 80% less expensive than hauling the material off-site to be processed elsewhere. So we proved that works at 3 different sites, and we continue to explore opportunities to expand this business and really make a significant impact on some of these waste streams that have been left behind. In the US alone, there's over 15,000 abandoned uranium sites. And quite frankly, it's time to clean it up, take the good stuff out, and leave unleachable, uncontaminated material behind, and leave the environment in a better place. So this example or the images here from MLA analysis of before and after, I think, again, show a really good example of how HPSA is performing before and after. This also illustrates the effectiveness when you have ore types of bimodal hardness. So here you're seeing quartz was coated with uranium-bearing carnotite. After HPSA, liberation's complete. We've got a cleaner material, more efficient separation, and a big step towards reclamation. Here we have an example of HPSA operating in a phosphate process. So this was both a batch and continuous pilot operation from November of 2022 into July of 2024. The results demonstrate a P2O5 grade increase of 4.7% with a P2O5 recovery increase of 2.9% and decreases in SiO2 and MgO. So the images you're seeing here again from MLA are really demonstrating how the apatite particles were coated in calcite, which is also a common issue in traditional circuits. And that translates into surface cleaning, boundary fractures within the HPSA, able to turn that around. So after HPSA, you can see the difference is quite dramatic. The apatite's liberated, calcite's fractured, and really, it's quite simply just a case of using smarter energy to unlock more value from the ore. In a separate, more recent on-site test, which happened earlier this year, we witnessed again a 15% more of P2O5 and over 50% less MgO in a regrind stage. So better concentrate, lower penalties, extremely beneficial from an economic standpoint across many of these case studies, not just phosphate, where you're able to increase profit margin per year into the millions, lowering operating expenses, earning a higher dollar per ton, and operating more efficiently. Taking a look at an example of a copper application here, and also a major boost. Here you're really seeing the impact of how we're able to liberate at a much coarser P80 than traditional grinding technologies. So you can see the side-by-side difference here. We've got copper minerals associated with quartz and orthoclase. After the target minerals are freed, floated, and just simply delivering better recoveries at a much coarser P80. And you see the impact of the grade increase of 8.4% versus 2.4%. So significant strides in copper testing thus far. Again, much more, many more applications to test, more materials from different geographies, but early indications, so significant efficiency gains, recovery gains across copper. If we look at copper nickel, a similar story here, where we're consistently able to outperform traditional methods. In one test, we saw more than 2% increase in nickel recovery and over 1% in copper. It's really a huge lift without changing the rest of the plant. From a graphite perspective, really it's all about purity and flake size at the end of the day. HPSA delivered coarser liberation without sacrificing grade. We've got cleaner separation, fewer fines, and the prospect of a more efficient flotation circuit. The graphite example is also what was used in the energy consumption example as well. So here we're able to really change the game for battery grade production, much more efficient, less energy draw, and significant increases in grades and recovery. Lithium, here's an example as well. Lithium can be a bit tricky and not so easy to process. We're seeing coarser liberation, reduced fines are helping with the downstream recovery. With lithium currently in such high demand, really every percentage point here counts, and HPSA is providing much more of them. Now let's talk a little bit about rare earths. These minerals are embedded in harder matrices, but the HPSA is using the base minerals themselves to liberate the valuable REEs. So you can see here where we are able to boost REE concentration from 29% to 95% in just one case alone here. That is extremely precise liberation. And you can really see if you compare the feed material graph here on the right, you're seeing the HPSA product reaching 95% in the -400 fraction. So we're really able to shift the mass into the finer fraction and liberate at a much more effective grade. And finally, if we take a look at zinc processing, when we're comparing to a traditional ball mill, the HPSA's delivered, again, superior selective liberation, higher grades, less waste, and quite frankly, a simpler circuit, and just in the end, a smarter way to mine. So I'm gonna pause there. We can go into Q&A. So again, thank you for the opportunity. I hope this gave you a great understanding of what HPSA is all about, how it can be integrated into an existing flow sheet, reiterating the fact that we have the ability to test both in-house and at site, and we welcome the opportunity to do that. If you think there's something here and an advantage for your process, for us to come in and do that for you.
Sam, I want to thank you for a very thorough and great presentation about HPSA. I think that as we look at the, again, recovery of materials through this process, the energy efficiency, all of the environmental pluses, I can't imagine that this company is not going to continue to grow and grow quickly. So it is time for question and answer, and it looks like we have one question in the queue, and if you and Tim want to take that one.
Sure. Just gonna.
Oh, there's two actually.
Okay, so I've got a question here from Jean. What is driving force for minerals separation? Is it separating in different fractions or only two fractions?
You want me to take that, Sam?
Sure.
Yeah, so I mean, the driving force for mineral separation is really the impact of the material on the material. We're going to get a much higher size reduction with the coarser material, where the finer material is more of like a sandblasting effect, where you're removing, surface impurities and things like that from the finer particles. But you're also, I mean, those finer particles are certainly going to have an impact on the coarser particles as well, but it's a particle on particle collision that's creating the separation. A lot of it's based on dual modal hardness materials, where one's harder or one's softer than the other. That doesn't necessarily play as much of a role in the finer size fractions of materials, where it's where you're actually it's a different type of more of like a abrasion, sliding impact, attrition type of impact with the finer particles. So you don't see as much of an impact in the bimodal hardness requirement from the finer side, but yeah, in the coarser size fractions, in say 150, 200 micron plus, you're going to see breakage along grain boundaries.
Excellent. And one other question, how much water usage is involved? Also for REE, the particle size is quite small. How does that impact flotation process?
Yeah, so the water usage is really dependent on the process. We can go with 0%, solids all the way up to say 55% solids. Really the limiting factor is what the slurry pump can handle. As a process improvement, we're typically just dropping this in as with whatever that percent solids is within the operation. So if it's 40% solids, that's just what we're going to be feeding to the HPSA typically. For our uranium operations and applications, a lot of those are in very arid climates. So water usage is certainly a factor that has to be in consideration. So we put these systems in typically with some type of an ultrafines recovery plant to recapture that water and send it back into the feed of the system, because ultimately it doesn't really matter how dirty the water is. Like, that doesn't actually impact the process. So the only water that you would lose as part of like a tailings or a reclamation would be in the dewatering screen oversize, so maybe at 12 to 15% solids, or 12 to 15% moisture. So that would be the water that you would lose. But then again, it's a high variation in the percent solids for the slurry concentration from 0 to 55%. And the interesting thing for rare earths and for lithium and any process where slimes and fines are a major concern around the downstream flotation and the process, it's really where our technology shines. And the reason for that is because we're really a liberation technology. Size reduction does happen, but we're basically just trying to figure out, how many collisions is it gonna take? to create the liberation that we're targeting. So we're not creating unnecessary size reduction per se. We're not necessarily driving towards a targeted P80. We're driving towards, a liberation target. And our process, the fines are basically following the water as part of the collision. So we're not creating super fines. So we're not over grinding basically. So in processes like lithium or rare earths where fines creation can cause major downstream implications and issues, that's where we really as a technology can shine, and where I think we'll get, large scale incorporation.
Thanks, Tim. I'm going to take a question from Christina. Christina's asking, what are the CapEx and OpEx benefits for a traditional mining company looking at Disa for this technology? So, Christina, I'd say in both cases, the benefits are significant from a pure dollars perspective. If you look closer at from an OpEx perspective, we don't have any large gear drives. We're not having to spend a lot of energy moving or rotating equipment. It's also much safer to maintain. We don't have to go into confined space to change liners, for example, or shut something down for up to 72 hours. The HPSA units themselves have multiple collision chambers, which you saw in one of the videos. If a nozzle were to plug, for example, there is a bypass in the distribution chamber, which would allow us to do maintenance on one collision while the 80% of the rest of the capacity of the plant is able to still operate in a safe, efficient way. So a lot less downtime, a lot less energy usage, no grinding media and chemicals. So, you couple that in with the reduced labor you're spending maintaining these, quite significant operating expense reduction. And I think we've got one last question from David. You mentioned clean several times. Can you define what you mean by that? So, Tim, maybe if you want to add a couple of comments.
Yeah, I guess I'm not really sure on the question. I don't know if clean means surface area where we're getting clean surfaces, especially from like tailings where they're oxidized. But if you mean clean by when I mean say you don't need clean water, clean technology. I guess from an environmental perspective, it's clean in the sense that, you don't have grinding media and it's much less power consumption and you're only, trying to liberate, not grind everything down to a target size. So, in that essence, it's very clean. There's no chemicals as well. So, it's clean in the sense that it's a very limited environmental impact. The other thing, with that is from an operation CapEx perspective, when you're looking at putting in like say a ball mill or a tower mill or those type of things, you're looking at significant foundation requirements. You're looking at a lot of environmental impacts around, just actually installing, those pieces of equipment. So we're also clean from an installation perspective, just because it's so simple and because there's no big loads and weights and vibration. The environmental impact for just the installation is clean as well. So I'm not sure if I answered the question, but I covered a variety of different angles, I guess.
Yeah, and that's what I was alluding to in mentioning clean technology a couple of times as well. It's a slurry hose in, a slurry hose out, very modular designs. You're not having to procure all kinds of material handling equipment. There's no dust. So it's a clean from a setup and installation standpoint, as well as the performance of the actual unit is providing a clean, liberated product in the end as well. We'll take another question here from Peter. Peter's asking what values of pressure is considered high. So really, Peter, it's about 100 PSI in pressure. You can imagine it's a centrifugal pump, centrifugal slurry pump. If you think about perhaps the Warman pump brand, if you're familiar with it, that is where the pressure is coming from that is sent through the impinging nozzles. So you're not talking about 2000 PSI like you would your power washer at home, for example.
We do have some time for some additional questions. If someone out there has one just at the tip of their fingers. Here we go.
Aaron asked, do you make your own pump? No, we don't. We source the pump from well-established OEMs.
As we're waiting for another question, I'd like to ask, how do you want the audience to connect with you with additional questions that they might have and or in wanting to be a part of what you're doing?
Sure. I mean, if you look over my shoulder, hopefully you can scan that QR code. So that's one way to connect via LinkedIn. Additionally, of course, visit our website or send me an email or Tim, and you can contact us directly. So website, the QR code, yeah, and happy to answer any other questions or provide a deeper dive into the technology one-on-one as well. So Melinda's asking, how many of these units do you currently have? So there's up to a half a dozen units that are deployed out into the field. There are units at third-party labs as well. So we do have third-party partners that are located globally, which can perform HPSA testing and help us just speed up the cycle testing versus shipping samples across the ocean and over borders and the like. And then we also have a fleet of units that we can deploy. We'll also ramp that up here with the WEA grant and have another number of units available to deploy later this year as well.
Another question here from Doug.
Doug is asking, how scalable is this? What is the maximum throughput per unit? So Doug, really the intention at the moment is on one of the slides I had mentioned, the next phase is reaching the 500 ton per hour mark. But in theory, it's really at the limitation of a centrifugal pump and the size of a nozzle that we could procure and manufacture. So I hate to say the sky's the limit, but it is quite scalable because we're using traditional components within our system, within our process, centrifugal pumps, valves, hose, nozzles. These are all things that lend themselves to a quite wide range of scalability upwards.
Another question from Jean.
The technology can process lithium brine. Tim, you want to cover that?
Yeah, there's no reason it couldn't. I think the question would just be, what would the benefits be? It certainly would go through the unit, and we certainly could process it, and there certainly would be collisions. So, if there's contaminants or things that you're looking to liberate, or there's a process improvement from, that agitation, we certainly can process it.
Any last comments that you would like to add here? Might give an opportunity for one last question, but it is getting close to the end of the hour here.
I guess just to reiterate for everybody, really consider HPSA as process improvement. It's not necessarily one-to-one replacement of traditional tech or similar tech. Think of it as a process improvement. We can take a slipstream from a ball mill. We can take a look at cyclone underfull. We can go in and do some remediation work and look at tailings recovery. So if you're looking to improve recoveries, increase grades, reduce your waste piles, HPSA is quite flexible and should be thought of as process improvement. If you're after process improvement, making your plant more efficient, then we're ready to test material. We're ready to come to site and to work with you. Don't just think as a one-to-one product replacement.
Again, Sam and Tim both, I want to thank you for being here today. Excellent presentation, very, very good questions from the audience as well. So a big thank you again from the Critical Materials Institute for attending this webinar. I want to remind you that this will be available in another week on our aimslab.gov/CMI site, as well as on the Critical Materials Innovation Hub YouTube channel. Next webinar will be on April 15th. Min Han Lee of Stanford University is going to present the vulnerability of raw materials to scaling quantum technology. Obviously, and as usual, it will be in the Critical Times newsletter so that you will be able to register for joining us again. We're always looking for new topics that are of value to CMI, just as today's topic. So please don't hesitate to let us know what else you would like to see in this webinar series. Once again, thank you for our audience, and also again, thank you to our presenter and Tim also joining to answer questions. We look forward to seeing you in April.
Thank you, everyone. Have a great day.